with my buddy and at this point frequent co-author Ludavic Renou, who's at Queen Mary. And then a couple of sentences. I just want to say that this is it's going to be a very straightforward theory paper. Some people might view that as a bug. I view that as a feature. But I personally think the contribution here is the framework and the questions that it lends itself to. So I'm going to make an attempt to try to impress that upon you as well. Okay? So let me give you a quick introduction. I'm going to use the term discrimination, so I don't want to get into a discussion, a big debate about what that means, but in this talk, I'm going to use the term discrimination to refer to the fact that when we observe the outcomes for two different groups who are otherwise identical, their economic outcomes differ. Okay? So when I talk about groups, what do I mean? I mean examples are men and women or blacks and whites. When I talk about economic outcomes, what do I mean? I mean things like wages, which is going to be the focus of this paper, mortgage rates, policing decisions, and so on. Okay? And it's well known that we actually do observe enormous differences in the outcomes for otherwise observably identical groups. So very broadly speaking, economists characterize discrimination in two categories. The first, which is going to be the focus of this paper, is what we refer to as statistical discrimination. And this is discrimination that arises because employers or decision makers have different beliefs, or they have differential information about both groups, right? So think of this as a good example of this would be the discussion about whether SAT scores are accurate representations of the abilities of minority groups, for example, right? That's a signal that decision makers use. The other category of discrimination is what's referred to as taste-based discrimination. I find that hard to say, so I'm just going to refer to that as bias. And what that just basically means is that the outcomes are different because people have some sort of bias or animus towards the disadvantaged group. Okay? So what the purpose of this paper is going to be is that I'm going to try to develop, or Ludo and I, we develop a non-parametric test. I'm going to, it'll be clear in the sense in which it's non-parametric, to test for bias using extremely basic data, okay? And the data we're going to use are going to be essentially wage distributions. Now, if we read, when we look at the popular press, what we often see is we talk about wage gaps. So these are differences in average wages, let's say between men and women or white and blacks. And when we read about this in the popular press, when non-experts talk about this, they often interpret wage gaps to be evidence of bias, okay? But this could be the result of perfectly rational decision making. So for example, if we think of, let's say the distribution of one group has more variance than the other group, and let's say wages are convex, we might see different average wages, even though decision makers are not actually biased at all towards the disadvantaged group. And our point of departure is going to be looking at a statistic like wage gaps, which are basically just comparing the first moments of the wage distribution, is throwing away a lot of information from the wage distributions, and we're going to try to use that. Okay? So I'm going to give you before I jump into the model, I'm just going to give you the question that we address so that you know where I'm going when I start describing the model. So consider two groups. I'm going to call them 1 and 2. And now what the researcher observes, and this is going to be the basic data that I was referring to, are two wage distributions. And I'm going to call them G1 and G2. So the talk has, I'm a simple man. Most of the things I write tend to be simple. So there's going to be very limited notation. I struggle to remember it, so I'm going to keep reminding you guys what it is. And it's going to be on most slides. So the G1 and G2, so the G is a letter you need to remember. So GI is the wage distribution of group I, and these are CDFs. So GI of W is just the fraction of workers who make wage W or less in group I, okay? And again, here I want you to think of two groups that are otherwise identical because I want to compare apples and apples. So think of people who work in similar occupations with the same age, with the same education and so on, okay? The question that we're going to ask is, when are these observed wage distributions consistent, or in other words, when can they be rationalized by a general reduced form model of statistical discrimination that I'm going to define on subsequent slides? And so I'm going to try to give you conditions on these wage distributions such that whenever those conditions are satisfied, we can explain them with our model, and conversely, when they are not, we cannot. And the purpose of this is that we're going to interpret rejection. So whenever we cannot explain these wage distributions as having arisen from statistical discrimination. So here, from differential information, we're going to interpret that as bias. So the point of this is to derive conditions, and when we reject them on the data, we use that as a way of inferring bias, okay? So our null hypothesis is going to be statistical discrimination, and rejections of the null, which are informative, are going to be evidence of bias, okay? So with that, let me jump straight into the model that I'm going to try to define relatively fast because we don't have a lot of time, okay? So this is going to be the model. So there are two groups of workers. I'm going to refer to them as I, there's 1 and 2. Theta I is going to refer to the productivity of a worker in group I, okay? Now this productivity is unobserved both to the econometrician or the researcher and to employers, okay? This is the true ability of the worker. It lies in some interval that you don't have to remember that notation, but it lies in some interval, okay? Theta I is drawn from a productivity distribution that I'm going to call HI. So that's the second letter you need to remember after the G, okay? A small technical point, which doesn't really matter, is that this distribution can be discrete continuous or be a mix of both, so it doesn't matter. So that's the first piece of the model. H1 and H2 are the two true distributions of productivities of the two groups of workers. The main assumption I'm going to make is that the average productivities across these two groups are the same, all right? So just the expectation of the true productivity of group 1 is the same as the expectation of the true productivity of group 2. Now, this seems to us, at least theoretically, is a natural starting point when we're trying to think about discrimination. These groups at least are comparable in some way, but I'll talk a little bit later about how we can generalize this, right? But I want to stress here that apart from the means being the same, these distributions are otherwise unrestricted, so in particular, one group can have fatter tails than the other or higher variance. Okay? Good. So employers, as I said, do not observe the true productivity of the worker. What they observe are some noisy signals of this productivity. So this is the sense in which it's a model of statistical discrimination. Okay? And so the employers observe some noisy signal. What is this signal? Think of this as you conduct an interview, you look at a CV, you look at reference letters, and the inherent bias that might be in these, or the noise in these signals that might be in all of those. Okay? These signals are drawn from some distribution. You don't have to remember that letter, but the only thing you need to know is that conditional on the true type of the worker, there's some distribution over observed signals. And the only thing you need to take is that distribution has an I subscript, which means that the signals can be different across both groups, okay? So when the employers observe a signal, what they can do is they can form a posterior distribution by Bayes updating. So everyone here is Bayesian. And so in particular, if they form a posterior distribution, they can calculate the expected productivity of the worker, okay? That is the expected productivity of the worker conditional on observing signal SI. Now, because SI is random, right, different SIs are going to lead to different expected productivities. I'm going to denote the distribution of the expected productivities as seen by the employers by FI. So that's the third letter you need to remember. So I'm going to refer to them as productivity estimates, and F1 and F2 are the distributions over expected productivities that are seen by employers as a result of this noisy signaling device, okay? Good. So now employers have seen a signal, they're able to calculate the expected productivity of the worker. Let me just say a couple of quick facts about Bayesian updating. Because F1 and F2 are formed by Bayesian updating, a couple of properties are true. The first is that these things have to be mean-preserving contractions of the prior, okay? That's a well-known property. And the second statement is that conversely, if I take any and I denote that, by the way, with this squiggle, with the 2 referring to second-order stochastic dominance, okay? And conversely, any mean-preserving contraction of the prior can be generated by some signal. All right, so there's just properties of Bayesian updating. Good. The last piece of our model is the wage function. So this is just a mapping. So after employers see the signal, they form a posterior productivity estimate, and they use the wage function to assign a wage to the worker. Okay? So it's just a mapping from the expected productivity seen by the employer to some number. Okay? And what I'm going to assume that it's going to be continuous and strictly increasing. The continuity is not so important. the strictly increasingness is. And otherwise, these wage functions are unrestricted, okay? Good. So in other words, an employer pays W of theta to a worker when she infers the posterior productivity estimate of this worker to be theta, all right? So if you now give me these two distributions of posterior productivity estimates, and you give me a wage function, I can calculate distributions over wages that I should see in the economy, all right? Let me pause here and say that the model is reduced. So when I said it's general because I'm making no restrictions on these distributions apart from the fact that they have equal means. I'm making no restrictions on the signaling technologies that for both groups, and I'm making no restrictions on the wage function. I should have said one thing. Notice that the wage function does not have an I subscript. So a worker with a expected productivity theta for both groups gets the same wage. So again, this is the sense in which it's a model of statistical as opposed to taste-based discrimination, okay? But the model is reduced form because I haven't told you where any of these objects come from, okay? And I'm not going to do that, all right? Good, so that's my model. So these are the letters you need to remember, the H, F, and G, and W as the wage functions, the 4 letters you need to remember, all right? Good. Our question is basically, as I started on the outside, is the opposite, right? Remember, our question is we observe these guys, and we're going to ask, when can we explain it with the model? So just to be formal about that, I'm going to say that the observed wage distributions G1 and G2 are consistent with statistical discrimination if they can be rationalized by our model. So again, just to go back to my picture, what does that mean? Given G1 and G2, these are things that we observe in the data. I can rationalize these if I can find the pieces of my model. What are the pieces of my model? 2 distributions over true productivities that have equal means. 2 distributions over, so 2 signals, which is the equivalent to say that I can find 2 distributions over productivity estimates, which are mean preserving contractions of the prior distributions, and a wage function that's continuous and strictly increasing such that given these pieces of my model, I get precisely the distributions I observe, okay? And so the question is going to be, when are these wage distributions consistent with statistical discrimination, okay? Let me just quickly discuss some features of the model. So let me try to big up our setting, okay? So the first thing is the model is general. So typically in settings of learning in the literature, people look at typically Gaussian distributions with Gaussian signals. So we don't require that. We're not restricting, our only assumption is on the first moment of the productivity distribution. So we're requiring equal means. I'll say more about that moving on. So we're not restricting higher moments. And as I'll talk about later, we can allow for unequal means in certain ways. I'll be clear about that, okay? We can allow for arbitrary statistical experiments for each group. We can, unlike the literature, allow for imperfectly competitive labor markets. What does that mean? So typically, what people assume is that if I think the expected productivity of the worker is theta, I pay her theta. So for economics, that's the same as saying that there's a well-functioning labor market, so people get paid exactly their expected productivity. We're not imposing that, so we're allowing for imperfectly competitive labor markets, okay? But I do want to flag one thing is there is an assumption that I snuck in there, which is wages only depend on the first moment of the posterior distribution. So the employer gets a signal, she forms a posterior distribution. In particular, you might want wages to depend on other things. For example, you know, Malish might have a higher mean than me, but he might have greater variance, so we might be worried he's going to burn down the building, okay? So and that might factor into our decisions, okay? And the last thing before I give you my main theorem is I am going to define what I mean by no discrimination in this model. So statistical discrimination is still a form of discrimination. And you can define this in a variety of different ways. The way I'm going to do it is I'm just going to say that employers perfectly observe the true productivities of the worker. Remember, that was the true productivity distribution. That was the distribution over posterior estimates. Okay, so when the employers, there's no noisy signaling. When you observe the true productivity of the worker, I'm going to refer to that as no discrimination. Good, so now we're almost, I can now give you my main result, but I'm going to give you one more definition that everybody knows, just so we're on the same page. I'm going to say a wage distribution GI strictly first order stochastically dominates a wage distribution GJ, and I'm going to refer to that as FOSD for short. I'm going to use the same squiggle that I had before when I was talking about mean preserving contractions, and I use a 1 now instead of a 2 because it's first as opposed to second order stochastic dominance. Well, GI strictly first order stochastically dominates GJ if the CDF always lies below and strictly below at some point. Okay? So with that last definition, I can now present essentially our main results. So I'm going to give you a bunch of statements. 10 minutes? Oh, I'm doing great. Okay. So I'm going to give you a bunch of statements, and they're all equivalent. All right? So the first statement is that I can explain the two wage distributions I observe with our models. In other words, they're consistent with statistical discrimination. A necessary and sufficient condition for that is neither wage distribution first order stochastically dominates the other strictly. Okay? So in other words, whenever these wage distributions are not ordered by stochastic dominance, it doesn't matter how large the wage gap is. So in other words, how large the difference in mean wages are, I can always explain them by just differential information. Okay? So that's the first statement. Now, for those of you who are familiar with these kinds of models, you might have realized that we have actually built a lot of redundancy into this model, and it'll become clear why we're doing this, right? So the next two statements are that there's a lot of things in the model that are overkill. So what is the first statement? The first statement basically, this third statement basically says that whenever two wage distributions are consistent with statistical discrimination, they are also consistent with statistical discrimination and the added restriction that the productivity distributions of both groups are the same. In other words, what this is saying is that because the signals are completely unrestricted, I can fix not just the means, but the actual productivity distributions of both groups to be the same, and I have sufficient flexibility in picking the signals such that I can generate any distribution over posterior estimates that I want. And conversely, whenever wage distributions are consistent with statistical discrimination, they're also consistent with employers perfectly observing the productivities of the workers because, again, I have complete freedom in picking the prior distributions, so I don't need the noisy signaling device. That adds nothing. Okay? Good. And of course, if I allow the wage functions to be group dependent, so if the W had an I subscript, I could explain everything. So in other words, within this framework, if I observe in the data that one wage distribution first order stochastically dominates the other, so it violates the model, I'm going to say that it's always going to be consistent with bias, so that's why I'm going to interpret rejections of our model as evidence of bias. Okay, good. Let me just make two quick discussions, maybe two quick comments about this. The first comment I just want to make is that what the redundancy sort of shows here in the redundancy results show is that allowing for different productivity distributions of the two groups has no added explanatory power. So a common explanation that people use for, let's say, the differences for some traits of men and women is that men have fatter tails. So even if women have the same or higher averages, men have fatter tails. And what we're basically showing is that this generality leads to no additional explanatory power. And what should be clear here is that if we instead now think of not that both groups have the same mean, but if we think of the case that the disadvantaged group may have a higher mean productivity than the advantaged group. So this is the sense in which we might think that somebody from a disadvantaged group, if they become a doctor, have faced so much adversity to get there, they might actually be better. So it's what we refer to as misallocation. There's evidence that, this is a recent paper that basically shows that in a large multinational firm, women tend to be a higher average productivity than men. We're all the same. Okay? So in other words, the same condition is also going to essentially reject that the mean of the disadvantaged group is actually not just equal, but higher than the mean of the advantaged group. Good. So I have 6 minutes. Let me give you a couple of pictures. So first thing is, I think it's a cool result. It's very simple. It's very clean and easy to state. But of course, first order stochastic dominance is a strong condition. So a natural question you might ask is, okay, Rahul, you have a nice theorem, but do we care? So what I'm going to do is, I'm going to give you a couple of pictures. This is a theory talk, so these are very suggestive pictures, okay? So essentially, these are pictures. Those are probably smaller than you can read, but I'll just tell you what you should take from it. So essentially, how would you take this model to data? One way you can take this model to data is you can look at, let's say, blacks and whites. You can take a bin of people who have the same education, the same occupation, the same age, and so on, and you can just plot the CDFs, right? Or you can run a statistical test for first order stochastic dominance. But of course, that's if you use, so here's a picture with census data. The problem with that is that there's zillions of bins, right? Because for every different value of the control variable, you have a new bin. So how would you do this in a way that, how would you try to illustrate this in a way that accounts for it? So these are some pictures that a buddy of mine, Prashant Bharadwaj, who's a faculty at UC San Diego, was curious to see if this would work in census data. Essentially, what you can do is you can run a quantile regression where essentially on the right-hand side, you can put controls and you can put a dummy for basically for race, all right? And you can run this regression at different quantiles, and if the dummy for race has the same sign, so in other words, if it's, you get a negative wage, so first order stochastic dominance is equivalent to wages for the disadvantaged group being lower at all quantiles of the wage distribution, okay? So if you run a quantile regression at different quantiles and the dummy for race is always negative, that's basically the same thing as saying first order stochastic dominance. These are pictures that run those regressions for blacks and whites in census data, in NLSY data with a bunch of different controls. The only thing you need to take from this is that those numbers are negative, all right? And that we have standard errors. The same thing holds for Hispanics, and as a sanity check, if we do it for Asians in 2021, this is no longer true, okay? So that's the only thing I want you to take from this. So I have 4 minutes, Larry. Perfect. We stand on the shoulder of giants. Let me try to give you a proof of one direction in the remaining 4 minutes and then conclude, all right? Good. So let me give you a quick proof of necessity because it's really that straightforward, all right? So what does necessity here mean? It means that if one wage distribution first order stochastically dominates the other, we cannot explain it with our model. So for contradiction, suppose that the wage distribution of group 1 does first order stochastically dominate that of group 2, and that we can rationalize it with the model. What does that mean? Well, we have these two wage distributions that are ordered. It must mean that we can find some wage function that's continuous and strictly increasing. If I use that wage function and I invert these distributions, I'm going to get distributions over posterior estimates. Because this is a monotone function, if I take two distributions that are ordered by first order stochastic dominance and I transform them with a monotone function, I'm going to get two distributions that are also ordered by first order stochastic dominance. Now, for me to explain, I have to also pick two prior productivity distributions. So in other words, I have to pick two distributions that are mean preserving spreads of F1 and F2. Now, because these are mean preserving spreads, these need not be ordered by first order stochastic dominance. But what has to be true by the martingale property of Bayesian updating is that the mean of the posterior has to be the same as the mean of the prior. So the mean of H has to be the same as the mean of F. Because these two are ordered by strict first order stochastic dominance, the mean of group 1 has to be strictly higher than the mean of group 2. That violates our assumption, okay? 2 minutes. So that's the simple description of this necessity. If I had 3 minutes, I would also give you some intuition for the sufficiency. But let me not do that. Let me jump straight to my concluding slides because I do want to talk a little bit about the broader agenda. So essentially, the key insight of this framework is that what we did is, so typically what economists do is they try to answer this question by using richer data, right? But what we're showing is that often, for example, for something like wages, it's really hard to find productivity data, so to get information about the true productivity of the workers, but we might still, these questions are still important, all right? And the way we get around this is we make what we think are reasonable assumptions on the productivity and the true productivities of the workers, and we use that to derive a non-parametric test. Now, whenever you do something parametric, at some level you're making some assumptions. The assumptions that we make are of different qualitative nature, but we view them as being inherently reasonable. But the assumption, there's nothing in what we're doing that necessarily has to be the right way to do it, right? So if we wanted to extend the framework, we could think of, okay, let's think of the true productivity distributions as lying in some convex set. In our case, we were requiring them to have equal means. We can have some wage function that depend on productivity distributions, and we want to impose some sort of structure. The structure we impose is that the higher the productivity, the higher the wage. But you could also, for example, have the wage function depending on other moments of the productivity distribution. So for example, there's a mean variance trade-off and so forth. Okay, 0. So basically, in a nutshell, you can define a general version of this problem, and you can try to figure out whether you can answer this question. And I will stop.
Thank you for that. Since we're running behind, we take one question while Giacomo sets up. Please.
It's a great talk. I was interested in learning, so when you remove or create essential responders, the process this typically leads to like, or it can lead to like fluorescence and power light or null. And I was wondering, I don't know, if you thought of your comments a little bit about like the power of your test or maybe how it would be changed.
So the question was, has he lost all the power of his statistical tests with these general non-parametric assumptions? Somewhat more politely asked than that, please.
Can I borrow your mic? So at least in what we do in our framework, power is not an issue because you can use census data. Right? Census data has a lot of observations. But you're right in saying that it depends on, we found it surprising that at least in setting this general, we can still, you can see from the pictures that even if you, the patterns are pretty clear. Now we don't have a lot of controls in those pictures because quantile regressions are very computationally intensive, so there are a few of them. But that's one of the challenges, that you basically, if we were to make the model more general, it would obviously weaken the testable implications. And so there's some trade-off there between the amount of generality we want and whether we think it's actually useful in practice. And that's sort of one of the exercises, right? So, but yeah, I'm not sure that was a good answer.
All right, thank you, Rahul.